Very good afternoon, Dr. Reddy, Professor Verma, my colleagues from DRDO, and ladies and gentlemen. Actually, a talk about propulsion, I start at a disadvantage because most of the time the highlight of such a presentation is the videos which show how a propulsion system works. You might have seen missile flights in TV or maybe in the videos in YouTube. The highlight of such things is essentially the sound and light show that you see, and that's where the propulsion comes in. But talking about propulsion, I will confine my talk to the propulsion that we make use of in our missile systems, because propulsion essentially is a way of transporting something from one place to another. Now, when I mention this, I will talk about what we do in the case of missiles. Now, just to give an idea, you might have seen the missiles on display at our exposition. The missiles vary in size from 200 millimeters to maybe 2 meters, this is 2000 meters. The same thing goes in terms of the kind of thrust that is produced. It's from a few kgs to hundreds of tons. The missiles have a specific requirement that they need to work at extreme conditions, especially the tactical missiles which are used in the battlefield have to work from in extreme weather conditions, in rain, sunshine, in temperatures varying from minus 40 degrees Celsius, especially for air-launched missiles, to plus 55 to plus 60 degrees Celsius. All these mean that the design and of these missile propulsion systems have to work within a certain margin, and that's where really the challenge comes. Now, when you talk about missiles, again, we have missiles which perform different functions. They could be, surface to surface or surface to air or air to surface. The idea of, as I mentioned, of the propulsion system for missile is essentially to carry the payload from the point where you want to launch it to the point where you want to take it. That's where your enemy or the system that you want to damage or destroy is. When we come to I'll just briefly mention the way we divide our propulsion system. First of all, let me say that so far the most effective propulsion system that has been used in missiles is chemical propulsion. That means the energy comes from the breaking or comes from the combustion of the fuel and an oxidizer. The oxidizer could be some oxidizer which is present in the fuel, or it could be something which is like the air itself. So this is what has been really been the proven technology. There are other kind of systems, energy systems like nuclear or solar, which are used, for example, in electrical power systems in satellites, but they are not of much use here because of the thrust levels that they can generate. They are pretty low, though they are very efficient. Now, talking about propulsion, we can divide them into the kind of fuels that are used. We have propulsion systems where the fuel is a solid. Where essentially, when I say fuel, okay, it's something that burns and produces hot gases, which when expelled through what we call a nozzle, it's essentially a tube through which the gases exhaust. It's a variable area tube, and that produces the thrust. What really happens is that, I think those of you who are mechanical engineers, they may know that basically when we say temperature, it's in a gas especially, it's nothing but the random kinetic energy that's available with the gas. So what we do essentially is that we take this random kinetic energy, that means the velocity could be in any direction, and on the average there is no specific direction. And when we pass it through this tube, we are giving it a direction. So what happens is that the random nature comes down, that means the temperature comes down, but the kinetic energy in a particular direction increases. And that's what gives the momentum for the gases to be thrown out, and that is what produces the thrust that we make use of. It is true not only for rockets, but also for air breathing systems. All this is chemical, mainly all the chemical thrust producing systems work in this way. So the fuel could be in the solid mode, where we could have a fuel where the fuel which can burn with an oxidizer, they are mixed together. They are one single piece. It could be that we also have systems wherein the fuel and the oxidizer are separated, and they come together only when you want to make them work, react, or combust together. So this is primarily liquid fuel systems. You might have seen the ISRO rocket motors. Some of their high efficiency rocket motors, like the cryogenic engine, is essentially a liquid fuel engine, whereas the solid rockets are used for the initial thrust. We also make use of air breathing engines. We make use of the standard air breathing engines are the turbojets, turbofans, which are used in our commercial aircrafts as well as in our fighters, but they are also used in small missiles. You may see some of them, for example, in the Rustam or in our cruise missile, they are used. As well as other air breathing systems like ramjets. They are called ramjets because they don't make use of the compressor which is used in a standard turbofan engine or a turbojet engine, and they work at supersonic speeds, and also scramjets, supersonic combustion ramjets. These are some of the things that are used in the missiles other than the rocket systems. Now, talking about the technologies that are involved, I would say that propulsion essentially derives its strength from almost all disciplines, both pure sciences as well as applied sciences and engineering. I think except for maybe nuclear energy, so at least so far. It derives, it needs information from all these cases. For example, we need to make structures which can operate as a rocket. The pressure under which these rockets operate, inside pressure, can vary from something like 50 at times the atmospheric pressure to, in some very specific cases, to 500 times the atmospheric pressure. The temperatures can vary from something like 2000, 1500, let's say in the case of gas generators, to 3500 and beyond. So you can see the extremes of conditions under which the materials have to essentially confine these hot gases. So we make use of high strength materials. Today we are using a lot of metals, metal alloys. We also use composite materials, carbon fiber with some sort of an epoxy resin. But these are areas where we need still more, let us say, information or research to improve these materials, to make them lighter, to make them fail gracefully. For example, it should not explode. If our design criteria, what we would desire to have is that even if there is a damage, let it leak, but let it not explode, because that can cause a significant problem for the people who handle this or the structures which are nearby. We have not still reached such stage, but this is something that we would look for. Similarly, when something hits this, let's say that in a battlefield, let's say a bullet hits this, it should not explode. If it just burns, it's okay. Or if there is a fire around it, if the casing could somehow unravel itself and then just allow the gases to leak, that would be the best thing. So these are some of the research areas that I would say are in the leading phase in our area. As I mentioned, one difference between our systems and, for example, other commercial launch vehicles is that when we make a system, a missile for example, we assemble it, we put it inside a casing, and like one of the earlier, I think it was a Hero moped when first came, they said fill it and forget it. So we do exactly that. We have to just load it, and almost, at least the propulsion system is concerned, there is no way to check its health. And for after 10 years, when the soldier pushes the button, it has to work. So the kind of reliability that is required, and for a one-time application, this is the thing which makes it different from other rocket systems, especially those which are used in the commercial area. So we need to know how each one of these materials behave as they age, what kind of deterioration in performance can happen, and this we need to know without the knowledge that 10 years down the line what's going to happen. There are methods, but there are also limitations to such methods. The other thing is the combustion itself. I mentioned about, when we say that, okay, we see combustion, for example, in our house, in a stove, or when we burn firewood. But the actual phenomena that takes place inside is pretty complicated. Now, the question is that why do you need to know? I mean, to burn wood, why do you need to know the real detailed mechanism? You light it up and give it sufficient heat, it's going to start burning. But the thing is that there are many cases where we need to operate systems at their extreme limits. For example, you might have heard about lean combustion to reduce the temperature of combustion, so that this is true especially for commercial aircraft, so that the pollutants that will not be formed, or the amount of pollutants will be formed will be very less. But then this has a penalty in terms of the instability of combustion. It can blow out anytime, okay, because of the stage of operation, and plus it can create instabilities, and that can create either oscillations of the combustor, or cause a structural failure, or even blowout of the combustor, which is not a desirable thing, especially for a missile system where you do not have such a control to relight it. Maybe in an aircraft you may have 1 or 2 chances for relighting, but we do not have. So this is another area why we need to understand. If you take a solid fuel like a wood, what happens is that there is a phenomena by which the heat essentially heats up the wood, and there are materials which will pyrolyze, or which will form gases, and these gases come out and burn. So there is a kind of combustion, burning taking place in a gaseous level, which in fact also drives also a combustion in a solid level. The same thing happens in our case also. We have, when the propellant, when it is heated, it produces gases, and it will also have solid particles like hydrocarbons, or it could be even metals to increase the temperature. And these combustion phenomena we need to understand, because the combustion, there are problems associated with this. In an enclosed cavity, that is what we have in the case of a rocket, these enclosed cavities can have their own resonances because of the acoustics. And if somehow the combustion, let's say, resonates with this kind of at the frequencies, then it creates a very large feedback of energy from the combustion to the acoustics, and this has been a very severe problem, and it takes a lot of effort to control. And so this is still one of the areas, I believe, in fact all over the world people are doing a lot of work to understand what goes on over there, because there are a lot of physical phenomena taking place. Things will melt, and then it will bubble, it will produce gases, and many such things happen. Now, I have talked about the material. Now, you know that I talked about the very high temperatures. Now, you need to protect the casing, for which we use insulating materials. We use what we call ablative insulating material, which essentially form gases which absorb energy. Now, design of these ablative materials is, again, because they are essentially not contributing to the energy to produce the thrust, but they are contributing to protect the casing. So it should be as light as possible. And we need to design very light, very efficient systems. You might have heard, one of the things which people have been using quite a lot is carbon phenolic systems. And now, if you read in NASA, for example, they have developed a foamy carbon phenolic system, which has reduced the mass, and they claim, in the case of Apollo spacecraft, when they re-entered, those insulation systems could be used only once. But now they claim these kind of insulations can be used 3 to 4 times. They can be repetitively used. So you see the amount of time and money saving that you will have. We also, because our systems have to be as light as possible, this is one of the areas that we need to work on, and we need to prove. Now, coming to combustion, again, the way by which you have combustion, if the oxidizer and the fuel are kept separately in the form of gases or in the form of liquids, is essentially that, you spray these. Now, why do you spray this? Why do you need to spray? Why do you just pour them together and, you somehow light it? No, it doesn't work. The reason is that the combustion takes place at the interfaces between the oxidizer and fuel. So you need to produce a large interface. You need to produce large area. And the only way to do that is to form spray, so that you present a large area of these reactants together. Now, the spray, again, the spray formation how a spray forms. There are a lot of engineering approximations to that, but we are looking at spray formation not only of just liquids alone, but if I have metals, for example, embedded in it, so that I can have a higher density and I can form a spray. So because of which I get more efficiency in combustion. So this is an area which is under a lot of, let's say, attention in our country as well as outside. Another thing is that even between gases, it's not very easy for them to burn. One of the problems in supersonic combustion is that when you have two gases, fuel and oxidizer, flowing together, they don't mix very well. Unlike the case of, if you look at your stove, it's essentially what we call a premixed combustion, because the air and the fuel mixes before it comes outside and burns, like your Bunsen burner. Okay, it's something like that. But we cannot have a Bunsen burner, because one of the things here is that the velocity with which these gases will mix in these conditions will be of the order of about 2 to 3 times the speed of sound. So if you want to give sufficient time for this, you need to give a very, very long combustor. So you need to have some methods by which you can mix this, and so that they can also react. Now this is another area which is of very importance. Now I'm just quoting a few things because I'm not really prepared for a specific talk, and I don't think the time is there for us to dwell in detail in this. But I would say, as I again said, in propulsion, I see all disciplines, whether it is mechanical engineering, whether it is chemistry, physics, whether it is electronics, everything, because we need to control all these things, for example. So everything has a part to play, and I believe that's one of the reasons why this field together, and we need more of you in the future. Thank you.